The goal here is to get a sense of what does it mean to even talk about learning from a theoretical perspective. You know, why can learning work, and what does that mean to learn something mathematically? And we're going to focus most specifically on supervised learning. We'll go back to unsupervised learning much later in the semester. So the one thing I want to really emphasize is that when we talk about machine learning, we can mean many different things. There are several types of learning. The one we'll focus extensively about is called supervised learning. And the general principle is the following. You're going to be given input data. And that input data for us is going to be a set of n vectors here, which we're going to call feature vectors. Okay, so these feature vectors, they're taking valued in a vector space. Typically, we'll view them as a d-dimensional vector space. Now, associated to these feature vectors, you have a label. Okay, the label is something that you attach to the feature vector. So as an example, the feature vector could be an image that you're getting, and the label is whether it's a cat or it's a dog. Now, the goal in supervised learning is to identify the input-output relationship between the training data, which is a set of pictures, say, which we represent by these feature vectors xi, and the label that are provided to you. Okay, so it's called supervised because for every feature vector, you're provided with a label. Okay, for every xi, you're provided here with a yi associated to that label. Now, the goal of supervised learning is to generalize what you learn from your training data. You're going to use your training data to come up with a guess as to what is the relationship between the label y to the input feature vector x, but then you're going to try that formula that you've inferred from your training data on samples, some feature vectors x that you have not seen yet. That's called generalization. You need to be able to predict whether an image is a cat or a dog on an image that you haven't seen yet. Now, so the supervised aspect comes from the fact that you're given the labels that go with the feature vectors. Unsupervised learning, in contrast, only gives you data in the form of the feature vectors. So you have n of them again, these xi, and what they represent is they represent an observation of phenomenon. So for instance, the xi's could be sentences that I'm speaking in French. And your goal here is not to figure out the relationship between that input data, which is a bunch of sentences in French, and a label, because it's not given to you. Your goal is to understand the structure that's behind the data. So for instance, you'd like to identify whether the French I'm speaking, either a grammatical, syntactical rule behind it. And these are things that you can infer even if you don't understand French at all. Because through repetition, in the form of all that training data, you'll be able to see patterns. Okay? So really, unsupervised learning is quite different from supervised learning. Supervised learning can be viewed as a way to do function approximation. You're trying to approximate a model. Unsupervised learning is really trying to infer structure. It can also be viewed, I guess, as an approximation, but there is no label involved in unsupervised learning. Now, of course, these are just two of many types of learning. And even though we're going to focus almost exclusively on these two, you'll see people talk about semi-supervised learning. That's a situation which is halfway between unsupervised and supervised. You're provided labels for some, but not all of the data. Active learning, that's a situation where you start with an image of a cat and a dog, you form a model, and then you say, oh, give me another image. And you get to choose what other image you want in a way that allows you to form your function or your model as quickly as possible. Online learning, you're provided samples on the fly, and you have to make decisions on the fly. Reinforcement learning, transfer learning, imitation learning. So all these are variations on the theme. They all have very specific tools, and we won't really have time to touch upon them. So unfortunately, if you care about these topics, there are other classes that dive very specifically onto these other topics. The reason we focus on supervised and unsupervised, I think they're super fundamental. It's not to say that they're more important than the others anymore. Okay? So let's try to talk about what we need to talk about supervised learning. So most of what we're going to talk about for the next month and a half is going to be supervised learning. Okay? So what do we need to talk about supervised learning in a meaningful mathematical way and define what it means to learn? Well, the first thing is we have to acknowledge that there's something that we don't know. And the something that we don't know here is in the form of a function. Okay, so that function here I call f. Okay, it's a function that takes a feature vector. The feature vector takes value in, it's a real d-dimensional vector, for instance, and gets a label. Okay, so, and here I guess there is a small typo. This should be vector x. I'll fix that in the slide. Okay, so that unknown function, we really don't know what it is. The goal is to learn it. And how are we going to learn it? We're going to learn it through data. So I'm going to use the cat and dog analogy a lot, in part because that's a very hard problem. That's very canonical in machine learning. So F is the formula that tells us if I give you an image, is it a cat or a dog? And what you have access to in supervised learning is you have access to what's called the data set. And the data set, we've already mentioned that very briefly, consists of pairs, and each pair contains the following. You are given a feature vector. Okay, so the feature vector could be an image, and you're given a label associated to that feature vector. And the label is the nature of the image, cat or dog, for instance. And our convention throughout that semester is going to be that you have a number of training points in your data set, which is capital N. Okay, so N is a number of training samples. Okay, so again, X, think of it as a picture, Y is your label. Now, if you want to learn, you need to be able to define what you can hope to learn. And the way we're going to define it is going to be by saying that we have a set of hypotheses, which we're going to call this calligraphic H, as to what the function could be. So what it means is that I'm not trying to learn F, the unknown function in vacuum. What I'm trying to do is I'm trying to find in a set of models that I like, which I called H, a model that is close to F. Okay? So understand, this is a very general way of putting the problem, because I could define H to be the class of all possible functions in the universe, in which case there is zero loss of generality in introducing H. But what people do in practice, for a reason that we're going to see very quickly, is they introduce restrictions on the class of function that they're willing to model. And still, that's very general, because the class H, for instance, could model something that is a deep neural net with an AlexNet architecture. Okay, that's a specific architecture for deep nets. And that would lead to a meaningful set of functions H, because a deep neural net tells you how you create structures, but it doesn't tell you the weight you put on the different links in your deep net. Okay, so you get a class of functions. So there's not really much loss of generality by us introducing H, and as you'll see, what H is actually has a huge impact on whether you can learn or not. And finally, what we need is we need an algorithm, something that is able to crunch the data set, knowing the hypothesis set H, and come up with a model or an H here in that set, calligraphic H, that explains F. Okay, so that's what I'm trying to represent slightly pictorially on the picture to the right. So I have the function F here. Okay, so that function here is unknown. That's what's really important. We don't know what that function is. We think that there is a way to distinguish cats from dogs, but we don't have an exact way of giving that function. We're giving a data set here. Okay, so we have plenty of pictures of cats and dogs. And we have a set H, which contains models or hypotheses, which are possible ways I think I can represent that unknown function F. And what the algorithm does, it takes H, it takes a data set D, crunches that, and outputs a G. Okay, so G is, I should be a little bit careful here, the function G here is an element in the hypothesis set H, and hopefully that's a good hypothesis. Your algorithm is able to find a good model that explains your data pretty well and is a good approximation of F. Okay, so all of that, I think, sounds extremely reasonable, that there's nothing controversial about what I've introduced here. And let me just give you a slightly more terminology. So in terms of terminology, people distinguish several cases depending on the nature of the labels. If the label is a continuous value that takes infinitely many values, we talk about a regression problem. But if the set of labels is actually finite, so cats and dogs, it's finite. We have only two labels. We talk about a classification problem, and when y is equal to 2, actually, we talk about a binary classification problem. Correct that. Classification problem. And what's important here, and I'm going to re-emphasize that over and over during these first few lectures, is that our goal in supervised learning is to generalize. meaning that once we have obtained a potential model from the class H using the algorithm and the data set, our goal is to apply that model to unseen examples. We need to be able to classify pictures of cats and dogs that we have not seen yet. And as we'll see, that generalization problem is quite intricate, and I'll give you a demo in Python at the end of this course to really put that in concrete perspective. Okay, so it looks like, that's pretty well defined here, but what I'm going to try to argue through a bunch of puzzles is that that model in itself is not nearly enough to properly talk about learning. Okay, even though everything I've done here seems very reasonable, I have a problem distinguishing cats and dogs. I'm trying to learn an unknown function through a data set and a set of hypotheses to model the unknown function. I'm going to claim that there's a lot missing in that model to talk about learning in a meaningful way.